So after all of these series that we've done with all positive terms to find out whether they converge or diverge, we had a bunch of different tests. Well, now we're going to go to alternating series, where they go positive, negative, etc. On these, there's only one test, and here it is, the alternating series test. And it says the series and this is what it would look like. So you've got -1 to the n plus 1. So when n is 1, you're starting out with a positive a1, and then when n is 2, you get a negative a2, positive a3, and then it keeps going. So that's what it looks like, and we can say it converges if and only if, and then you give the reasons. First, all the a sub n's must be positive. In other words, if all these a sub n's are positive, then it really is going to alternate. So basically you're just saying it has to really be an alternating series. And then 2, the a sub n plus 1 has to be less than a sub n for all n greater than some big N. So it doesn't have to happen right at the beginning of the series. Just like with all series, those first so many terms don't really affect convergence. But after a certain point, what this is saying is all the terms in absolute value have to be getting smaller. And then lastly, the limit as n approaches infinity of a sub n must go to 0. So just like with positive terms, we had the nth term test that said a sub n had to go to 0. This is true also for alternating series. You can't really be adding up things that still accumulate. So, since this is the only one, the only test we have, we should probably prove it. So if we look at one of these series, a1 minus a2 plus a3 minus a4 plus a5 minus a6, and you keep going, you can see there's different ways that you could combine things. You could combine them like this in pairs, and what you would see is every pair in here is positive because of this statement right here. Because the terms have to be getting smaller as you go from a1 to a2. a1 minus a2 is going to be positive. a3 minus a4 is going to be positive. So what we have is a bunch of positive terms. So the more terms you have, the bigger the sum is going to get. So that means the sequence of partial sums is going to be an increasing sequence. And if you pair this differently, if you go a1 minus a2 minus a3 minus a4 minus a5, that's still going to give you the same thing you have right here, a1 minus a2 plus a3 minus a4. Now we see that whatever we start with, we're subtracting more and more positive things away from that. So that means this sequence of partial sums is bounded above by a1. We know that the sum is less than a1. So because you have an increasing sequence that's bounded from above, we know that it has to converge. Not necessarily to A1. It probably won't converge to A1, but something a little bit less than that. So that is pretty much the proof. Obviously, if you had an odd number of terms, you wouldn't be able to pair them up exactly evenly. There'd be one term at the end, but then since the limit of a sub n approaches 0, that last term is not going to really affect that convergence. So that's a proof of the alternating series theorem. Now, let's give an example of an alternating series. What if you have n equals 1 to infinity, negative 1 to the n plus 1, 1 over n. This is also called the alternating harmonic series, because without the alternating in there, that's the harmonic series. 1 plus a half plus a third plus a fourth. So this, when you look at it, when n is 1, you get a positive 1 minus a half plus a third. And if we want to know whether that converges or not, we could say, oh, it's an alternating series. I can sure see that it's an alternating series, so it passes the first part. Do the terms seem to be getting smaller in absolute value? Yes. 1, a half, a third, a fourth. It's pretty easy to see that they keep getting smaller. And lastly, does the limit as n approach infinity of a sub n, which is 1 over n, does that go to 0? And yes, it sure does. So by that, I can say by the alternating series test, this series does converge. Now, I wonder what it converges to. That always would be an interesting thing. Can I find out anything about what this adds up to? Well, let's just try something. What if I went 1 minus a half? I just took the first two terms. Then it's going to be plus all the rest of that stuff. So if I only took these two terms, I'm going to have some error over what the actual answer is. So I'm concerned about what the error is. I know this right here is 1/2. But how big is the error? Well, the error itself is equal to 1/3 minus 1/4 plus 1/5 minus 1/6 all the way to infinity. But again, if we pair things up, if I pair 1/3 minus 1/4, 1/5 minus 1/6, all of these terms are positive, which means our error is positive. So our answer is too small. We know our answer has to be bigger than 1/2. And if I pair this up differently, very similar to how I did in this proof up here, what I see is my error is 1/3 minus all these positive things. So I know I have a positive error, but it's less than 1/3. So that means my answer has to be between 1/2 and 1/2 plus 1/3, which is 5/6. So my answer has to be somewhere in between there. I've done a pretty good job of figuring out about what that answer should be. Now, if I went and added one more term, what if I went 1 minus a half plus a third? Then I've got 5/6 plus an error. But let's see what my error is going to look like this time. My error is now going to be from negative 1/4 on. So my error is going to be negative 1/4 plus 1/5 minus 1/6 all the way on. And if I factor out a minus sign, I get 1/4 minus 1/5 plus 1/6. I can see that I have the same type of thing going on in between here. I have 1/4 minus 1/5 minus 1/6. I can see that my error is going to be less than 1/4. And I can see that it's going to be negative. So this time, I know my answer is 5/6 is too big because I have a negative in front of this. So I know that my answer has to be between 5/6 and 5/6 minus 1/4. So between 5/6, and if I take 5/6 minus 1/4, that's 10/12 minus 3/12 is 7/12. So now I know my answer has to be somewhere between 7/12 and 5/6. So anyway, the reason I did that example is because this is just an example of what we can do in general with alternating series. There's the Alternating Series Estimation Theorem. Alternating Series Estimation Theorem. And what it says is, if you have an alternating series and you stop after a certain number of terms, the error in absolute value, because we're more interested in just how big it is always going to be less than the first term omitted. I think you could see this in both of these. On this one, the first term I omitted was 1/3, and the error was less than 1/3. Down here, the first term I omitted was 1/4, and the error was less than 1/4 in absolute value. And also, we found out here, when we omitted the one that began with a plus, the error was a positive. When I omitted the first term was a negative term, the error was a negative number. So I can say, and the sign of the error is the same as the sign of the first term omitted. This is going to become a pretty important theorem, especially when these series are something that we're really trying to get as close to the actual answer as possible. We're going to want to know how many terms to use. So let's just give one more example. Say I have the series 1 minus 1/2 plus 1/4 minus 1/8 plus 1/16. Basically, n equals 1 to infinity, -1 to the n plus 1 to make it alternate, and then you have 1 over 2 to the n. I think you can see that this is a geometric series, and r is going to be -1/2. So, what if I only took the first 3 terms to estimate what this is going to be? 1 minus a half plus fourth is 3/4. And I know, because this is a minus, that this is too big. And the error is less than 1/8. So that means I've got to be somewhere between 3/4, which is 6/8, and 1/8 less than that, which is 5/8. Well, this is 0.625, and this is 0.75. So I've really gotten it down to my answer has to be in a fairly small band. Now, for this one, we actually know how to find the answer to this. And that's why I picked this example, so we can check what is the real answer to this. Well, it's a geometric series, so if we take the first term and divide it by 1 minus r, then we can get the exact sum. So you get 1 over 3/2 or 2/3, which is 0.6 repeating. And that definitely is in between there. So obviously you wouldn't use the alternating series theorem for a geometric series, but geometric series are about the only kind that we really know a formula to find the exact sum. Okay, just another definition. So, if a sub n is a series, n equals 1 to infinity, an infinite series, and the summation n equals 1 to infinity of the absolute value of all the terms converges, we say that the original series converges absolutely. So it converges absolutely if it converges as all positive terms. If a sub n itself converges, but it doesn't converge with all positive terms, then we say that the summation of a sub n converges conditionally. So we're going to want to know sometimes whether a series converges absolutely or conditionally. Now, if you take a series of all positive terms, then it can only converge one way. It can only converge absolutely, because they're already all positive terms. So if it converges with an absolute value in there. It's only alternating series that may converge conditionally or may converge absolutely. For example, say you take -1 to the n plus 1 times 1 over n. That was the series that we did over here. And we found out that it converges by the alternating series test. But what would happen if you took away the fact that it's alternating? Then you would just have 1 over n. And we know that that's a p-series with p less than or equal to 1, which diverges. So that would mean that this series right here converges conditionally. It only converges when it's an alternating series, not when it's a non-alternating series. Now, what if we took -1 to the n plus 1 of 1 over n squared? Now, if we looked at the series as all positive terms, it would just be 1 over n squared, which is a p series with p greater than 1. Therefore, it converges. So we didn't really need this. This series right here, we would say, converges absolutely. I'll give you some examples on the next board. But there's one other theorem, and I'm not going to prove this, because it kind of makes sense. If a series converges absolutely, then it converges conditionally. So if a series converges absolutely, then the series converges. And that kind of makes sense, because when you start to throw minus signs in, it's going to help things not go to infinity versus one that has all positive terms. So I don't have too much room, but I'm going to just throw one quick example. What if you had sine squared of n over n squared? Now, or just say it was the sine of n. The sine of n over n squared. We know the sine values, the sine of 1, sine of 2, sine of 3, some are going to be positive and some are going to be negative. So we can't use any of the proofs that we've already learned before today. And we can't use the alternating series theorem because it's not alternating. It's just got some negatives and some positives. But what can we say? We can say that if we took all the positive terms, say we made this all positive, we could compare this series to 1 over n squared. And we know that this converges, and we know these terms are smaller than here because the sign never gets bigger than 1. So therefore, we can say that this one converges, because we know that it converges absolutely, therefore it's going to converge as an alternating series. Okay, so I'm going to give you 6 examples, and not only are we going to be learning what we learned today, but reviewing a little bit on all these series tests, because we're now done with series tests. And I want to try to show you how you have to attack series in general. So, with all these different tests, which one do you do first? So we're going to find out whether the series converge absolutely, conditionally, or whether they diverge. So, if I start out here, first I have to find out if they converge absolutely. So I'm even going to forget that this is an alternating series. Let's just wipe that part right out. And what does the series look like? It looks a lot like the series 1 over n. But I can't use the comparison test because these terms are less than 1 over n. So I have to use the limit comparison test. So I say rho is the limit as n approaches infinity of this term divided by this term. When I divide by 1 over n, I get so the limit equals 1. And 1 is a number, then it's not 0. Therefore, they compare favorably by the limit comparison test. And 1 over n diverges. Therefore, this whole thing diverges if it doesn't have the alternating in it. So I know it doesn't converge absolutely. But does it converge conditionally? Well, It's an alternating series. We only have one test. So, does the limit of these terms, does that go to 0? Well, n squared over n cubed, it does go to 0. So that part of the test passes. But we also have to show that these terms get smaller and smaller. And this is the hardest part of the alternating series test. So the only really way to do that, in this case, is to set this up as a function. So if we just look at x squared over x cubed plus 1,000, the function is going to be the same thing as the series, except this is for all real values and this is only for integer values. So if I can show that this function is decreasing, I can show that the terms of the sequence, or of the series, are decreasing. I mean, of the sequence of the terms in the series. So basically, how do I find out where a function decreases? I have to take its derivative. So I go low d high minus high d low all over low squared. Well, I'm not going to even write it because that's always positive. I can just look at the numerator, and the numerator is 2x to the 4th plus 2,000x minus 3x to the 4th, or x times 2,000 minus 2x squared. And the denominator we know is positive. So what do we see here? We've got this, x is always positive. This is going to be positive for a while. So the function's actually going to be rising. But once x gets to a certain point, for the rest of the time, the function's going to be decreasing. So we had to go to all that trouble to show that these terms, a sub n plus 1, are always going to be less than a sub n. This function is decreasing, so these terms of the series are going to be decreasing. So that was quite a bit of work, but I can now say by the alternating series test it passed all 3 of the parts of the test. Therefore, this series does converge as an alternating series, so it converges conditionally. Okay, now that really tested a lot of what we've learned over the last 5 lectures. And I'm also going to say one other thing, and I've never let students take shortcuts. But in this case, you see by far the hardest part of the alternating series test is to show that these things are decreasing. And I can tell you from experience, and it just kind of makes sense, that if the limit goes to 0, almost always it's going to be a decreasing, the terms are going to be decreasing. So I've let my students get away with not doing this part of the test and just show that the terms go to 0. As long as they keep in their mind that yes, that other part really has to be satisfied. And I'll get to an example of that in a minute. Okay, much easier problem right here. The very first thing you're going to do is the nth term test, because the nth term test works both for series that have all positive terms and it's a part of the alternating series test. So I can just take the limit as n approaches infinity of 1 over 10 to the 10th. Even though that's a really small number, it's not 0. So what you're going to be doing is you're going to be adding up terms that never really go to 0. And even though they alternate, you're never going to get convergence. So you can say right away that this one diverges. And you could either say by the nth term test, or you could say by the alternating series test, because it doesn't pass that the limit as n approaches infinity of 1 over 10 to the 10th, a to the n, it does not equal 0. Okay, another one. Again, since we do have to know, if I only had to know whether this converges, I would just use the alternating series test and say, yes, the limit as n approaches infinity of 1 over n cubed minus n does go to 0. As n gets big, these terms are going to go to 0. So by the alternating series test, if I don't make you prove the terms keep getting smaller, I can say that this one converges. But that only shows that it converges conditionally. So the first thing I'm going to do is just look at the series without the without the alternating part in. And what can I compare this to? I can compare this to 1 over n to the 3/2, because it's the square root of n cubed. So I'm just going to go straight to the limit comparison test, and I'm going to take rho to be the limit as n approaches infinity of this divided by this and if I ignore the lower powers of n, I get n to the 3/2 over n to the 3/2 is 1. So this series compares favorably with this p series, therefore it converges. So this one doesn't need the alternating part. So I would say it converges absolutely. This one only converged conditionally, because without the alternating series, it looked more like 1 over n. This one, without an alternating, it looks like 1 over n to the 3/2. So it really didn't need the alternating part, therefore it converges absolutely. Okay, so try this one. Again, remember, it doesn't matter where I'm starting. I wouldn't want to start out at 1 because I'd be dividing by 0. So I'm going to, again, ignore and just look the alternating part and just look at the series like this. And what can I compare that to? I can compare it to 1 over n, which we know diverges. And since the natural log grows so slowly, these terms in the denominator are going to be smaller than these terms. So these fractions are going to be bigger than these fractions. Therefore, I can just use the comparison test and say that this diverges, which for our case means that this does not converge absolutely. But now we can go to the alternating series test and take the limit as n approaches infinity of 1 over the natural log of n. And even though it grows slowly, this does go to 0. So by the alternating series test, especially if I don't make you show that these terms get smaller and smaller, we can say that it converges conditionally. I'll just put converges conditionally. And this one wouldn't even be really hard to show that the terms keep getting smaller. If you go to 1 over the natural log of 6 to 1 over the natural log of 7, you can see that these terms do keep getting smaller. So here's an alternating series, but I don't have a summation. If you wanted to put a summation, you could factor out a 4. You could put that it alternates. And then you could put the term in. Well, you could put 1 over, and it looks like it goes 1/3, 1/9, 1/27, 1/3 to the n. Except you'd want to go to the n minus 1, or else you could start at a different value of n. But you want to make sure when n is 1, you're going to get a positive number, and you want this just to be 4 times 1. So I think you can see that it works. So right away, we can see without the alternating part, you have a geometric series. It's 4 times the geometric series, and the r value here is 1/3. Therefore, it converges without the alternating part, so we can say that this one converges absolutely. Okay, one last one here. The summation n equals 1 to infinity of a sub n. But a sub n is different depending on whether n is odd or even. So it starts out at 1. So what's a sub 1? 4 over 2. And then you go to n equals 2, so n is even, so you get -1. And then n is 3, so it becomes this one, plus 4 over 4, and then minus 2/4, and then n is 5, so you get plus 2/3, and then is 6, so you get minus 1/3, and it keeps going. Now, what do you see here? That's 1. 1 minus a half is a half. 2/3 minus a third is a third. And you can see if you kept going, you're going to get this series, which we know is 1 over n, and we know it diverges. So that would be the answer. It diverges. But what do we see here? If we take the limit as n approaches infinity of a sub n, in this case, it goes to 0. 4 over something getting really big goes to 0, and the same thing here. So both of these terms do go to 0. So it passes. You have an alternating series that passes this test, yet it ends up not converging. So I had to go and really search to find a series where it would pass 2 parts of the test. The limit does go to 0, but yet what happens is these terms are not getting smaller. Look at 1/2, 2/3. In absolute value, these terms are not getting smaller. So it failed the second part of the alternating series test. So that's why I say it is possible to happen that you need to go through and show that. I just don't think in general that it's worth doing it every time. But always keep in back of your mind that this is an important part of when we prove the theorem. So the terms do have to be getting smaller. The a sub n plus 1s always have to be less than a sub n after a certain point. And this is not going to happen in this series. Anyway, there's a lot in this lecture today because it's not only teaching you about alternating series, but it's showing you what you have to do if you're attacking alternating series and have to tell whether they converge conditionally or absolutely. So anyway, in the next lecture, we're going to find out why we've been doing all this thing with infinite series and how it fits in a little bit with calculus. So, take care.